We can use the Datapath controller approach to design the microarchitecture for a CPU. CPUs repeatedly perform a fetch, decode, execute. They fetch the next instruction from memory. They decode the instruction to determine what operation it describes. They execute the instruction to perform the operation. The von Neumann machine doesn't make an inherent distinction between instructions and data. A memory location that's fetched for execution is treated as an instruction. A memory location that's fetched for a data operation is treated as data. This means that, among other things, we can write a program to generate data and then cause the CPU to treat that data as instructions. This is one way to breach the security of a computer system. A thread is a flow of execution through a program. A classic CPU executes a single thread. Some processors provide simultaneous multithreading that allows the CPU to switch between a small number of threads. The CPU keeps registers for each active thread. If one thread waits for a memory access or other operation, the CPU can switch to another thread to keep itself busy. A microarchitecture is a logic design for a computer. An instruction set architecture may have several different microarchitectures at different cost performance points. We'll use RISC-V to illustrate how to build a simple microarchitecture to execute instructions. RISC-V instructions have been carefully crafted to follow a model of execution that can be efficiently implemented in the microarchitecture. Fetch reads the current instruction from memory at the location pointed to by the program counter. Decode interprets the instruction in additional fields. It reads any necessary source registers. It also assembles an immediate operator from the fields in the instruction. ALU performs operations using the arithmetic logic unit. Memory reads or writes memory if necessary. Writeback writes a result to its destination register if necessary. We'll look at the datapath and controller for several categories of instructions. We'll first design a separate controller and datapath for each instruction, then put them together. Here's an integer register operation. The instruction is first read from memory. The two source operands are read from the register file. The appropriate function is performed on the source operands based on the func3 field in the instruction. No memory operation is needed. Writeback writes the result to the destination register. The program counter PC is incremented by 4. This data path allows the execution of the integer register operations. This is an integer immediate operation. One source operand comes from the register file, while the other is an immediate that must be assembled from the immediate fields in the instruction. As before, the program counter is incremented by 4. Here's the data path for the integer immediate operation. The data path and controller for jump and link are very different. A specialized unit to extract and assemble the immediate value is an efficient implementation. The immediate used to compute the target address of the jump is a combination with the current instruction address. The immediate is used to compute the target address of the jump in combination with the current instruction address. The PC is updated and the destination register is written to the destination register. Here is a data path for the jump and link. The jump and link register instruction differs from JAL by forming the target address from an immediate and source register RS1, followed by setting the least significant bit to 0, which can be performed using a small amount of added logic. Here's the data path for jump and link register. A load forms the effective address from the source register RS1 and an immediate. The memory stage is used to read the memory. The resulting value is then written to the destination register RD. The PC is incremented by 4. Here's the data path for the load. A store forms the effective address from RS1 and the immediate value, as with the load instruction. The value to be written comes from RS2. The memory stage writes the RS2 value to the effective address in memory. The PC is incremented by 4. Here is the data path for store. We're now ready to create a controller that executes all of these instruction types. The fetch and decode operations are shared. The succeeding stages depend on the results of the instruction decode. Not all instruction types use all of the stages. The shared data path can be built by adding multiplexers for selecting sources and registers to separate stages of execution. The PC update logic shows why we need multiplexers. The PC value can be updated in any of three different ways. Increment the current PC value by 4, add the immediate value to the current PC value, add the immediate value to a target address from RS2. We can build two different block diagrams, one that uses two adders and another that uses a single adder. Here's an overall unified data path with the PC update logic shown as a single block for clarity. The placement of registers must first break any combinational cycles in the data path, which is a basic functional requirement. Registers also help to balance the delay across the stages. The clock period is determined by the longest delay from any register output to any register input. Registers can be moved across logic to equalize delays. In some cases, registers are added to break a long delay path. Thanks for watching.